Howdy everyone, I'm Brandon and welcome to our second talk of CoffeeShop Astrophysics this semester. So tried to move things online, trying some new stuff out, so just let us know how it goes. So CoffeeShop Astrophysics is a group of graduate students at the University of Wisconsin-Milwaukee, specifically in the CGCA, the Astrophysics group. And we just like giving talks, we like sharing our enthusiasm with some of the things we work on and the things we enjoy with everyone else. So if you're watching this, you're enjoying it, please leave a like, but if you have any ideas for future talks, please put it in the comments below. If you're in the live chat, you can put it there, or if you have any other questions about anything else, feel free to send it to us. So today we're going to talk about exotic telescopes. So these are just telescopes that are different than when we normally think about telescopes, putting a lens and looking up in the sky. A lot of these use completely different techniques to see completely different messengers and different things in the sky than what we may be used to. So talking today is going to be me, and I'm also going to be joined by Gabe. We're just excited about some of the things that we work on and just really want to share it with you. So first, let's have a primer about some of the different messengers in astronomy. So normally when we think about astronomy and looking up at the stars, we think about seeing visible light, and that's what humans have been doing for thousands of years. People looking up, what do they see? Or after we've invented telescopes, you see with a little bit more precision, you see a little bit further out. But nowadays astronomers can see the whole spectrum, the whole electromagnetic spectrum of light, and see all the way from gamma rays down to radio waves, and that's given us a lot more information than we've ever had before. We can also see exotic things like neutrinos. We'll talk about those a little bit later, and also gravitational waves. And so some of those have been, especially with gravitational waves, we've only been able to do for a few years. So these are incredibly new and modern techniques. And there's also a whole set of other things that we could potentially see with space, like cosmic rays and alpha and beta particles, but we won't get too much to that in this talk. But there are a lot of things that now we've expanded upon in astronomy.
So as Brandon mentioned, today's topic is exotic telescopes. But before we actually talk about any exotic telescopes, I want to give you a little bit of background in non-exotic telescopes, otherwise known as telescopes. As you may have heard in a previous talk, or maybe you're hearing it now for the first time, what we think of as light is a lot more than just what we can see with the naked eye. Light covers an entire spectrum. It's classified by how long its wavelength is. And so the good old visible light that we all know and love, and that we can see with our eyes, well, that only covers an incredibly narrow region of this full spectrum. So sure, if we want to view objects in space in this region, we could just look up at night. We also have built plenty of telescopes to view space in these optical wavelengths. But we also use telescopes to view space in ways our eyes could never see, such as in the longer wavelengths over here, or in the shorter ones over here. The Earth's atmosphere also plays a very large role in what light that we can and cannot see. What we have here is a plot of what percent of our light the atmosphere actually lets through at a given wavelength. And so anywhere you see brown, that means that the light at that wavelength is going to be completely blocked by the atmosphere, and it's never going to get to us. So you can see the visible light, well, it makes it through just fine, as it should. But coverage in the infrared region is going to be a little spotty. And if we want to look at space over here in this region, or over here in this region, we're going to need to use telescopes out in space. And we do have telescopes such as Chandra out here that looks in the X-ray region. There's just a couple other things to note, though. Thank goodness for this whole block of brown over here to the left. The fact that our atmosphere blocks all of this high energy radiation, it means that you're not going to instantly roast when you walk outside. And this little sliver here next to the purple, well, that's why you all need to wear sunscreen. What you will notice, though, is that there's this huge section of light, of the light spectrum, that can be clearly transmitted through the Earth's atmosphere. This right here that's boxed out, those are radio waves. And we can actually learn a lot about our universe by taking advantage of this gap here to look at space in tons and tons and tons of different wavelengths. What exactly is out there for us to see? Well, for one, we have pulsars. Pulsars are rotating compact objects in space, and they're commonly viewed in the radio spectrum. They're super important for current studies in gravitational waves, a lot of which are done actually here at UWM. Another example would be the cosmic microwave background, which is sort of like a heat map of the early years of the universe. And we're talking really early, like a couple 100,000 years after the Big Bang early. The CMB, now that's something we would have never been able to detect using optical telescopes. It's only possible with radio ones. And then just as an aside, it's a little funny to note that the two things here, the pulsars and the CMB, they were both discovered totally by accident while scientists were using radio telescopes to look for completely different things. But anyways, there are plenty of interesting objects out in space that we can only see in the radio spectrum. There are, however, plenty of other objects that we can see in both the optical and the radio spectrum. Take this ball, for instance. What is it? Is it a star? Is it a galaxy, an alien, a UFO? Actually, it's just Jupiter. Jupiter imaged with a radio telescope. We can look at objects in space like this in two different ways, and it gives us a more complete picture of their behavior. So what kind of telescopes can we use to detect radio waves? Well, the shorter the wavelength of light, the smaller the aperture that you need to properly resolve the image. So for light in the visible spectrum, something the size of a human eye should work great. And this really shouldn't come as a surprise to anybody. Radio waves, however, are much longer, and we're talking like millions of times longer. And they're usually coming from sources much, much further away from the Earth than sources for our optical telescopes. So we're going to need considerably bigger receiving dishes, like the large telescope that you see here. It's located in South Africa. What's the downside, though, of using radio telescopes? Let's just consider this situation. You have your own little radio telescope out here, it's ready to take data, and here's a nice, happy little radio wave that's coming in from space for you to observe. And all you need is for this wave to reach your receiver, and then maybe you'd be able to learn something new about, nope, sorry, the Packers just scored, and here's your top 40 channel, and there's also a talk show, and don't forget your GPS. The point is, we use radio waves for a lot of different purposes in our daily lives. And so as far as radio waves go, it's crowded here, and a little bit difficult to detect the ones coming in from space, when we've got so many frequencies here on Earth that are already being used. And another issue that might arise, radio waves cover a large spectrum of wavelengths, and if we want to detect longer waves that are further away out in space, we'll need a bigger aperture, and then bigger, and then even bigger. And eventually we're going to reach a point where if we try and build a large enough standing telescope like this, we just won't be able to properly engineer the support, and the whole thing's going to collapse, and then that'll cost a whole bunch of money, and nobody's going to be happy about this. So if we're really limited on the size of the dish that we can support, are we just doomed to miss out on all of this cool science? Well, the answer is no. And the solution is, we'll just use the Earth to support it. The idea is that we're going to find natural craters, find sinkholes, depressions in the Earth, and we just use them to help build an incredibly sturdy base for an enormous radio dish. Take, for example, the Arecibo Observatory located in Puerto Rico. Using a natural sinkhole there, they're able to build a dish that was over 300 meters in diameter, and it opened up a whole new spectrum of radio waves that we can study. And just as another aside, Arecibo, the observatory is actually not doing too well right now. They had a couple cable failures within the last month, and so things there are quite precarious to make sure the science can keep going on, and so everybody just please send your good vibes that way. But why not go even bigger? There's the 500-meter Aperture Spherical telescope in China with a diameter of, well, yes, you guessed it, 500 meters. And it again uses the natural crater-like landscape to help support the massive dish. But now we have a problem. There's still a whole lot of the radio spectrum left to be explored, and it looks like the only way that we can get there and see it is to find bigger and bigger craters to build in. There's only so many available craters like this that we can find. And many aren't going to be big enough here on Earth, so what really are our options? Well, there's one option I'll propose. We can just wait for a meteor to strike Earth. They're notoriously good at putting holes in the planet. The whole process might be a little bit messy, it could be windy, there might be some light rain, but otherwise, we just wait for the meteor to hit Earth, we'll deal with the whole apocalyptic fallout thing, and then just plop a big old radio telescope there. Sound good? Obviously, there are some issues with this plan. The meteor could just land in the ocean, and then we all got stressed over nothing. And if we can't find big enough craters here, what are we supposed to do? Well, there's plenty of craters on the moon. Let's just go there. Enter the Lunar Crater Radio Telescope. This telescope was initially proposed back in 2018, and the name pretty much speaks for itself. We just go pick an enormous crater on the moon, around maybe 3 to 5 kilometers in diameter, and then fill it with the biggest radio telescope this side of the solar system. This would open up observations to a whole new range of the radio spectrum and would let us view parts of the universe that we had otherwise never before been able to see. Question remains, which crater do we pick? The plan is that the telescope would go on the far side of the moon, the one that we're never able to actually see from here on Earth. It's going to be the practical solution, as it'll completely avoid all that pesky noise that's coming out from the Earth. And also, the far side of the moon has considerably more craters than the near side, so we've got more spots to choose from. This leaves us with another practical problem. How in the world are we supposed to build this thing? This would be a huge undertaking to engineer. We can't just go duct tape some construction vehicles to a rocket and then just fly them off and dump them off on the moon. The far side of the moon also isn't really the most comfortable place for you to be spending your 8-hour workday. So sending people there is going to be totally out of the question. The proposed plan goes like this. We send a probe to the moon, and that probe contains the telescope receiver and a few anchor points they call axles. Before landing, these axles and the telescope will actually separate. The telescope will go land in the center of the crater, and the axles will anchor themselves into the rim of the crater around the diameter. The rover, with the telescope, will actually have a few other things besides the actual receiver. It'll contain some sort of wire mesh that the plan is it'll be pulled over the entire crater to create the full aperture of the telescope. When it lands in the center, it'll deploy a few guiding wires that are connected to this wire mesh, and likewise the axles will have some other guiding wires with a lock that they'll be able to roll down the sides of the crater. Those will lock together and link with the guiding wires from the telescope rover, and then they will drag the wire mesh back up towards the crater rim, and that will complete the construction of this telescope. Sounds pretty simple, huh? When exactly should we expect to see this telescope in action? Well, NASA just received early stage funding for this project back in April of this year. But as for when the project gets fully approved, no idea. And then they would need to begin construction. And then they would need to finish construction. And then maybe, it would finally be ready to begin operations. But the point is, this is going to take a long time before it's ready. But the point is, the idea is out there, and people are trying to work on it. And one day, we might actually have a giant radio telescope on our moon. And for those of you out there who may have certain concerns about starting high-tech developments on our moon and where it may potentially lead down the road, I unfortunately have nothing more to say.
I guess everything's good. I don't know. So thanks for that, Gabe. So now we're going to move to the other end of the electromagnetic spectrum. So now we're going to talk about gamma rays. So gamma rays are incredibly high energy light. So they're very, very dangerous, more dangerous than things like ultraviolet. So they can cause things like cancer and even worse things to humans. But these are going to be coming from the most energetic events in the universe, not from just some light bulb shining, but things like binary neutron stars smash into each other, or maybe even just like a supernova. So with how dangerous they are, you'd think that we have to put all these protections on the Earth to stop it. But in fact, gamma rays can be stopped by a piece of paper. So with light, there's a relation between how energetic it is and how much it penetrates. So radio waves can pass through our house, no problem. We use them to communicate with cell phones, but gamma rays get stopped by essentially anything. So we have this atmosphere, blocks it, so we don't have to worry about being destroyed by the gamma rays that hit our Earth all the time. But that does mean if we want to detect gamma rays, we really can't do it on the Earth, so we have to do it in space. So enter the Gehrels Swift Observatory. So this is an experiment run by NASA. It's a satellite in space, and it detects essentially gamma rays. But it's pretty special compared to the other gamma ray experiments. So it really can be described in one word, and that is... it took a while to go. It takes so long for it to come up. That's not fast at all. Okay, so Swift can be described really in just one word. It is fast. and it's fast at a lot of things. It's really fast at slewing compared to really any other experiment out there. It can have these momentum wheels that can turn it at incredibly fast speeds, but it is also really fast at follow-up. So what does that mean? So Swift doesn't just detect gamma rays, but it also detects other wavelengths of light too, like X-ray, ultraviolet, and even visible light, the ones we're used to seeing. So why would it do this? Well, imagine this. You have a very energetic event in the universe. You have something emitting gamma rays. So it's incredibly high energy. So kind of like a coal that you let sitting there for a while, it's going to cool down and start emitting less energetic light over time. So if you have this event that creates gamma rays, it will likely create light in other spectra in just a little bit if you wait. So when Swift sees gamma rays, it also tries to detect other things like X-rays and ultraviolet, and it's seen a number of these interesting events where it's able to see this afterglow after the fact. And this has given us a whole host of information beyond just detection in gamma rays. Also, Swift is incredibly precise in its localizations and makes it incredibly useful for follow-up for other experiments, like what I'm involved with LIGO. It's able to detect where something comes from very precisely, where LIGO basically says it's on the sky somewhere, maybe in a little patch if you're lucky. So what Swift does, it has a random pattern of opaque material over some gamma ray sensitive material, and depending on the direction, it will shine a different pattern on the detector cells below, and so you'll be able to reconstruct what direction it's coming from, based on that pattern. So when it gets the direction of the gamma rays, it's able to turn and be able to use its other instruments with it, which have really precise localizations on it. It can see in a very narrow cone, it can point it right at this event and can tell exactly where it is. So lastly, I want to talk about neutrinos. So neutrinos are a very different messenger of information from the cosmos than light. So they are a particle. They actually have a little bit of mass. We actually didn't even know if they existed for the longest time, and then we didn't know if they had any mass at all. But they do have a little bit of mass, but they move incredibly fast. So they're created in nuclear processes like happen in the sun, or even in really big energetic events like supernova. But neutrinos don't interact with matter much. In fact, most people call them ghost-like because most of them will pass through you. In fact, a ton are passing through you. Hundreds of billions or even trillions are passing through you right now, and they really aren't doing anything to you. So how could you possibly use them to detect anything in space? So there's a few neutrino experiments over the Earth, but I want to talk about a really special one called IceCube. So IceCube is just straight up built on the South Pole. It's just right on there. And it uses the ice under it as part of the detector. It's actually run by the people that are in the University of Wisconsin-Madison, our sister college. So one interesting ability of IceCube is able to actually track individual neutrinos. It's actually able to say where individual neutrinos, what direction they're coming from. It's because it has a number of these long strings that are able to aid in detecting neutrinos. And how they do that is they actually look at light that gets emitted by these neutrinos. So why would neutrinos emit light? Okay, so let's go over that. So when a neutrino is going through the Earth or going through the ice, almost all of them are not going to be detectable. They're going to go pass right through. In fact, you need light years of lead to expect a vast majority of them to actually interact, light years long. So when that neutrino goes through and passes it through the ice, it might trip on it essentially randomly and create a charged particle like an electron. It's like, sitting on the street of New York City and just waiting for someone, through all the people that are walking, just waiting for a random person to trip. I mean, that's how unlikely these sort of things are. But with so many neutrinos, there is a probability of this happening. When you have hundreds of billions and trillions of neutrinos, there's a small percentage of them that will interact with the matter, will interact with the ice. And when they do, they bump into it and they'll create charged particles like electrons. So these electrons are moving really, really fast because the neutrinos are moving really fast. They're actually moving really close to the speed of light in a vacuum. And some really interesting effects are going to happen because it's moving so fast. So something we need to note first is that the speed of light is slower in water and therefore in ice due to stuff getting in the way. So when light's going through, it has to essentially kind of bounce around. There's stuff in the way. It can't move as fast as it would be in a vacuum. So we can see effect of this by, if you put a pencil in a glass of water, you'll notice that it looks like it's being bent or misshapen in some way. It's because water passing through when it's going through a certain speed and then changing to a different speed is going to cause a bending of light. So the reason that happens is light's going a path to minimize the time between 2 points. So it's the same thing if you have a lifeguard running on the beach. He's trying to get someone in the water. He'll actually run more on the sand compared to the water because he's faster in it. So when you have these two mediums with different speeds, the fastest path will actually be a bent one, and that's exactly what water is doing here. Interesting things happens when something is going faster than the speed of the medium it's in. So in the case of an airplane moving in the air, there's a speed of sound. When an airplane moves faster than the speed of sound, a sonic boom occurs. So something we have to know is that also charged particles create light when they move. I mean, that's actually how radio towers work. You just take electrons, you move them up and down, and it actually will create radio waves going off. So when you have a charged particle created by these neutrinos after these particle collisions, zooming near the speed of light, it creates a ton of light. So when you have these charged particles created by these neutrinos hitting into these ice, and then they're moving faster than the speed of light in ice. Remember, we haven't violated special relativity or anything because we're really not going faster than that max speed limit of the speed of light in a vacuum. But when you have these charged particles moving faster than the speed of light in ice, they create a specific type of light called Cherenkov radiation. So Cherenkov light has a very specific spectrum. It's actually very blue and even has a lot of, part of it in the ultraviolet range. So you can see an example of this if you actually put a nuclear reactor underwater. But the strings in IceCube can essentially look for this very specific type of light and know that had to have come from a neutrino collision. Go back, retrace that, and actually can tell, yeah, that type of neutrino came in, it came from this angle, came from this, likely came from that source. So then you can use that information and be able to trace back, say where it came in the sky, maybe another experiment say, oh, we saw a supernova there. You can combine this information to tell you, and it tells you a lot more than any of these individual experiments by themselves. So this actually happened once, not with IceCube, but we've detected neutrinos coming from the same place as a supernova. It was the event 1987A. It has marked a huge start for multi-messenger astronomy, and essentially is a lot of what I do personally for my work. What happens when you see an event with two different types of light or just two different types of messengers? You get a lot more information than either of those events individually. Thanks everyone so much for watching. We really appreciate it, especially with all the crazy things going on in the world and us trying to pull together all this in a very different format than usual. So check our social media for any updates for future talks. Let us know how we did in the comments below. Give us a thumbs up if you really like this, and subscribe if you want to see more. Yeah, thanks for joining us. We'll see you next time. Bye.